Can I start now, say?
Yes, you can.
Okay, good evening, guys. I'm from Group 5. We are going to present on predicates logics. Next slide, say. Okay, so with our objectives, by the end of this unit, we should be able to explain the concept of predicate logic, also use the concept in writing logical statements. Next slide, say. Then introduction to predicates. The definition: a predicate function is a sentence that contains one or more variables and becomes a statement when specific values are substituted for the variables. We represent a predicate by a letter followed by the variable enclosed between parentheses. For example, p of x, then q of xy. Next slide, Sam. Then you have to note that the truth value of a predicate depends on the value assigned to its variables. For example, just like what we did when we were doing propositional logics, a statement becomes true or false when we assign a value to it, so that we can determine if the statement is true or if it is false. Next slide, say. Okay, so the example that we have over here, let P of x denote the statement x is greater than 3. What are the truth values of P of 4 and also P of 2? Then the solution that we have over here is we obtain the statement P of 4 by selecting x denoted to 4 in the statement x is greater than 3. Hence, P of 4, which is the statement 4 is greater than 3, is true. However, P of 2, which is the statement 2 is greater than 3, is also false. Next slide, say. Then we also have another example over here. Let Q of xy denote the statement x is equals to y plus 3. What are the truth values of the propositions Q of 1, 2, and Q of 3, 0? So our solution over here, for us to obtain Q of 1 of 2, the set x is equals to 1 and y is equals to 2 in the statement Q of xy. Hence, Q of 1, 2 is the statement 1 is equals to 1 is equals to 2 plus 3, which is false. The statement the statement Q30 is the proposition 3 is equals to 0 plus 3, which is also true. Then next slide, say. Then with predicate logics we have quantifiers. The first quantifier that we have is the universal quantifier. Then the definition: the universal quantification of P of x for a particular domain is the proposition that asserts that P of x is true for all values of x in this domain. They are denoted by the symbol upside A. Maybe I can put it that way. It's an upside A. So we say that one is for every value in x, that value is true. The next slide, say. Then with the universal quantifier, let P of x be a predicate and D be the domain of x. A universal statement is denoted as follows: all of x, P of x. That's how we write and how we denote our predicates using the universal quantifier. Next slide, say. Okay, so the example that we have with the universal quantifier, example 1, we have let P of x be the statement x plus 1 is greater than x. So here we want to see if the values in this set are true or false. So we're going to say let P of x be the statement x plus 1 is greater than x. What is the truth value of the quantification x of px where the domain consists of all real numbers? Then the solution that we have over here, because P of x is true for all real numbers, x is the quantification xp for all of x, P of x is true. Next slide, say. Okay, we are now on example 2. Let Q of x be the statement x is less than 2. Then what is the truth value of the quantification all of x qx where the domain consists of all real numbers? Okay, remember we said with the universal quantifier, we are saying everything that is in the set Q of x is true. So the solution that we have over here, Q of x is not true for every real number x, because for instance, Q of 3 is false. That is x is equals to 3 is a counter example for the statement all of x qx, that all of x qx is false. Next slide, say. Okay, so we said we have two quantifiers when we are dealing with predicate logics. So the second quantifier that we have is the existential quantifier, denoted by that E over there. So observe that the statement existent x px is false if and only if there is no element in x. Sorry, if there is no element x in the domain for which P of x is true, that is, the existent x, Px is false if and only if P of x is false for every element of the domain. Next slide, say. Okay, so with our existential quantifier, we have, okay, we have let Q of x denote the statement x is equals to x plus 1. What is the truth value of the quantification, the existent x in Qx where the domain consists of all real numbers? Then the solution that we have over here is Q of x is false for every real number in x. The existential quantification of Q of x, which is the existent x in Qx, is false. Next slide, say. Okay, now we are talking about negating our quantified expressions, that is negation of all of x, px, as well as the existent x in P of x. Then we will often want to consider the negation of a quantified expression. For instance, consider the negation of the statement. Every student in your class has taken a course in calculus. This statement is a universal quantification, namely O of x in P of x. So here we're only saying for every student in your class has taken a course in calculus. It simply means that this statement is true and everything in this statement is true. So we represent this one using the quantifier, the universal quantifier. This is all of x in P of x. Next slide, sir. Then the negation of this statement, when we are now negating the statement, it reads, it is not the case that every student in your class has taken a course in calculus, this is equivalent to there is a student in your class who has not taken a course in calculus, and this is simply the existential quantification of the negation of the original proposition function, namely there exists an x negation of p of x. Next slide, say.
So I don't know, Tim, if you are getting this. Are you all well with this?
I'm not.
Give us time to.
I'm sorry.
We can move on. Wombo. Timbo pezisa.
It's breaking up.
Hello. Thomas,
Okay.
make a query low.
Yes, sir. Thank you, sir. I think she's moving very fast. She needs to give us time.
Okay.
When she should ask if we have any questions. I think that will be better.
Okay, hanzi shield ari kumhanya. Unomboita uchiexplain uchitibvunza kuti hatina imwe mubvunzo here.
Ndiri kutyira network se inogona kungodropa anytime.
Usati vamwe wako vanenge varipo, handiti vamwe here, ndambona sungwana mublessing wavemo, ndaona uchijoina.
Okay, so can I proceed now?
Okay, you can.
Slow down.
Already on slide 14.
Okay, guys, do you have any questions from where we are now? Okay, so I think I can proceed.
Just for a quick recap, and it triggered anonzi my predicates, and it on a predicates, you are just saying it's a function, right? Just a simple function that you have there with some certain variables. So it's just a function of maybe x, or it's just a function of xy, or it's just a function of xyz. So it's a function of either a single variable or of multiple variables. And we call it what? P of x, or we can even call it what? Q of x. And then from there, it will actually become a statement whenever you substitute a certain value, right? So for the initial instance, it will be not having the truth value, since it's just a sentence with what? With the variables. So you cannot determine its truth value, like be it true or what, or false. So after putting some certain values for the variable, you can now tell that this one is what? Is true or false. That's the part of the predicate itself. And then from there, there is the quantifiers. There is the quantifier. Then we are talking of a quantifier. We're just talking of words which actually represent what the quantity there. And normally we have two quantifiers, which is the universal quantifier and then the they exist. Then on the universal quantifier, what you do there, you've got the for all statement on the universal quantifier. It's like you are referring to everything in the domain or in the universe, or that you are considering that this predicate is always true for every value in the what? In the domain. That's the universal quantifier there. So when she was saying for all x in the domain, then p of x is what is true. Is just saying whenever if we take any value in the domain and we plug it to our function, we always get what? The truth value is what? Is true. If you go with the they exist, now the existential, quite the existential predicate. So it's what? It's they exist. So it's no longer for every, it's no longer for all, but it's now for some values in the domain. Then p of x is what? Is true. So it's like we are just saying for everything that we have in the domain, we've got some values that if we plug them in the function, we always get what? We get the truthiness of the function is what is true, though we have got some other values that if you plug, then the truth value of the function will become what? Will become false. So the they exist doesn't consider all the set. Just take the part of the domain as the values that give us what? True if we plug them. And then she goes on to the negation of the quantifiers. Like if you negate the universal quantifier, it's like you're just saying there exists something that there exists maybe x in our domain, that if you put that x in that function, it's going to give us the false value, or the truth values of is what is false. That's why you see that when you negate the existential quantifier, the let me see if I've got any highlighter. Just like here, okay. If you negate, let me see if I've got a highlighter here. Okay, just like to go with the green. Okay, so let me see the negation. Okay, just like here. So you're saying the negation of for all x, then what? Then p of x is just the same as there exist x such that if you put that x in p of x, you will get false. That's why we have got this flipping part, this one, the negation. You are negating what? P of x, which means you are saying for all of x in what? In a p of x, it's no longer what? It's no longer true, because we are negating that statement. So you are saying for all p of x in what? In x, or in what? In our domain, then p of x is what? Is false. So it's just the same as saying there exists x in our domain such that p of x is what? Is false. I don't know if you are getting it. Because remember here we were just saying for all the values in what? In x, our p of x is what? Is true, and then we just negated that statement, which means we are now saying for every x in our domain, p of x is what? Is not true, which means there are some values in what? In our domain that if we put them on our function, then the value that we get is what? Is false. So I don't know if you are getting now this identical part. We are saying this statement is the same as this statement. So whenever you negate this one, it's the same as go to the existential quantifier and negate the p of x there, just like that. I don't know kana tave pano pamwe chete ipapo.
Yeah, we are together, sir.
Okay. So I think Shelter, you can now proceed.
Okay, thank you, sir. All right, we are now on slide 15.
We're on slide. I think that's the slide that you were. Isn't it the slide? Shoot. Hello, Thomas.
I think Miss Shelter is raising her hand there. There's something to say.
It was just like that. Sharon, Shelter,
Maybe the network is shut here out.
Yabva yadropa.
Haisiri network panatiza. Vamwe vacho varipi?
Varipo anatafadzwa.
Hapanatiza, vamwe vacho anenge adzoka. Network yake anenge adzoka. Wamwe wacho aripiko? Wamwe wacho ari muchingopedza basa ranga rabatwa naShelter.
Okay, say I'm back.
Okay. Tanda kutokureva
Sorry.
kandichiti pamwe watiza ka.
No, my network is very, very bad.
It's okay.
Okay, let me proceed. We are now on the De Morgan's law for quantifiers. So you're talking about the negation, the equivalent statement, when is negation true, and also when negation is false. So I'm going to start with the first one. Negation of the existent x, such in P of x. So when the equivalent statement is true, we also write like all of x, negation of P of x. Then what does this mean when the negation is true? For every x, P of x is false. Then when it's false, there is an x for which P of x is true. Then I'm moving on to the next one. Negation of all x.
Apa unenge wamhanya. Unenge
Alright.
wamhanya. Kuti
Let me
izvozvi.
come again.
But truth, this
Let
one
me
is
come again.
this one is the existential statement, and this one is the universal statement. They are all equivalent. And when is the negation true and when is false? Those who have a table yako, anditi? Those
Yes.
who have a table yako. Yeah, and then you explain kuti zvii zviri kuitika panapa, anditi? Because apa ukabva watomhanya uchitoenda kumwe toita kutoshaura kuti zviri kufamba sei.
Okay, let me try to explain. All right, just like say, I've already said, when you have these two quantifiers, like for example, there exists an x, right? The existential quantifier. We just take the opposite. The universal quantifier is the opposite of the existential quantifier. So, like for example, when these ones are equivalent, we just look at the existent x of px. Then the opposite is the for all x in px. Now we are saying these two, they are equivalent. I have tried. Should I move
I've
on
not
now?
I didn't hear anything there.
Okay, so like we are
Let me
saying,
just okay.
like we are saying, we have the existential quantifier, right?
Yep.
And when we are negating it, right, we are saying the opposite. The universal quantifier is the opposite of it. So when you are negating, are we negating it? Yes. For example, when you are negating, when is negation true? For every x in px is false. That's how we write it. Like for example, in the first line.
Yeah. Now it now makes sense. We are saying whenever you have there exist x in P
Yes.
of x such that P of x
Yes.
is true, and then you negate that statement. What it means, that statement is equivalent to what? To this statement. But for every value in our domain, then P of x is true. It doesn't now stand, and it is equivalent to what? For all values in x, P of x is what? Is false. Just because tine some value irimo mukati momo irikuita kuti P of x aite false. Saka all of that is what? Is false. Then we are saying when this negation is true, if this negation is true, remember this negation have got, it's also what? Truth value, which is true or what? Or false. Saka truth kana negation iyi kana ikaita true, if this negation is true, yekuti there exists P of x such that x is what? Is P of x is what? Is true. Kana this negation tikangonegeta panapa tozoona kuti no zviri kubuda izvi, tozoona kuti zviri kubuda zviri true zveshuwa tanegeta. Zvakureve kuti for the universal quantifier yatati for all of x then P of X is true. Yeah, for all or for every X in our domain, then P of X is what? Is false. Why? Because true panapa pataita negation panapa. This one is what? Is true pata negator. Then when this one is false, then we are saying there is an X for which P of X is what? Is true. That's the explanation which is there. So it's now on the part of understanding it, but that's what the table is trying to portray. That's what the table is trying to say there. When this one is true and when this one is what? Is false. So whenever the negation of there exists X such that P of X is what? Is true. If that negation is what? Is true, then it's as good as you are saying that for every X in our domain, then P of X is what? Is false.
So zvirikuoneka sei?
Anzodiko pana rudo kutaura. Ana rudo kutaura, hanzi kudiko. So we can go on to the second part, which says for O of X, then P of X is true. So to my values are X are domain. My values are X are domain. My super function in it are true. But I negated that statement, which means you'll be saying for all my values are X are domain. My values are X are domain. Pana P of X. Achabuda true. What I negated that statement. It's now what? It's now false. Surungoreva is what? Now there exist some values in X. Kuti kana tingaise muna P of X, then P of X anoita chi? Anoita false. Indeed. So if this statement is true, which means there is an X for which P of X is what? Is false. Because to my values is muna X, to this function or this universal quantifier tikai negate, then truth value yacho yobuda true per statement iro. Zviri kureva kuti zvonizvo. Pane some values atori mudomain ekuti kamaise pafunction pedu, then the result will be what? Will be false. Those panapa if this one is true. And whenever this one is false, P of X is true for what? For every X. Because remember, panapa negate and it for all of X in our domain, then P of X is what? Is false. But negate because at first that is true. So but negate now we are saying this one is false. So if the truth value of that claim that this one is false, negate, ikabuda iri false, zvinongoreve kuti zvonizvo iri kuramba kuti ese mavalues ari mudomain aX tikamaisa munje chobuda chiri false. So in other words tingoti ese mavalues ari mudomain aX tikamaise pana P of X, chinhu chedu chinobuda chiri always true. Saka ndo zviri panapa. Amengana zvakuonekwa zviri kureve table yedu tiri kurevei.
No, I think, sir, excuse me.
Yes.
I think this is clear. Maybe along the slides, I don't know whether we have some examples down there. I think what's complicating people is the English itself. Because you negate, you say it's equivalent at the same time, and then you say it's negation is equivalent. People, it confuses a bit. I think with the time we're using the examples, understand. Yes,
Okay,
I don't know.
okay. So okay, I don't know if there are some examples here. I think there are some examples.
Thank you.
Yeah, sure. Anokwanisa kungotirwira ma-examples asara.
Okay, thank you, Say. Then we have example 1. What are the negations of the statements? There is an honest politician and all Americans eat cheeseburgers. Then the solution over there, Let h of x denote x is honest. Then the statement there is an honest politician is represented by the existent x. I can't see properly. All right. The existent x in hx, where the domain consists of all politicians. The negation of this statement is negation of existent x, h of x, which is equivalent to all of x, h of x. The negation can be expressed as every politician is dishonest. The note in English, the statement all politicians are not honest is ambiguous. In common usage, the statement often means not all politicians are honest. Consequently, we do not use this statement to express this negation. That is the first example. Next slide, sir. Okay, so with our example 2, what are the negations of the
Excuse me,
statements?
Excuse me. I'm raising my hand. This is Shelter.
Yes, dear.
Sorry for that. Can we go back to the previous slide? Sorry. Yes,
All
yeah,
right.
thank you. I think I got lost here. This statement says there is an honest politician. Okay, this is the first statement. The second one is all the Americans eat cheeseburgers. What is the domain here? Can you explain where do the domain principles get in here for me to understand what's going down there?
Okay, for example, here, the domain here is all politicians.
Okay, all politicians, there is an honest politician, okay? There is an honest politician. So, okay? Yeah, go on, go on. Hello? Hello?
Asi Shelter asimo. Shelter.
Maybe it is a network.
Andiri kuona senge arimo ka.
Maybe.
Amene kuti zvii zviri kuitika. All right, abva abuda. Asisimo. Okay, what's happening here is that, all right, ari kutishaye kudzoka. What's happening here is that we've got two examples here. We've got two examples. We've got this part. There is an honest word, an honest politician, and then there is this one. All Americans eat cheeseburgers. So only focusing on this one, which says we've got a domain of what? Of politicians, and we are saying out of all the politicians, there are some politicians who are honest. So this statement is claiming that there exist some politicians within all the politicians who are honest. So those so this statement we are saying it is true that there exist X such that H of X is what is true. And then when you negate that statement, when you negate this statement, just like this, it's equivalent to this statement. Like for O of X such that H of X what is false. Those are funny because you are negating now that there are some honest politicians. So what it means now is that every politician is what? Is dishonest. Both member politicians are honest. Then negate that statement. So it's equivalent, like you are now saying all politicians are what? Are dishonest. Those are zero. So it's, yeah, so that was the example there. That was the example. Like you are trying to say, whenever you negate something in an external quantifier, it have got its corresponding identical part in the universal what? Quantifier. So we negate it here, and then we can also express that negation in what? In universal quantifier.
So,
Yeah.
so you're saying that it explains the other table on top.
Exactly. That's what we are trying to explain here.
Okay, now I got it. Okay.
Yeah.
It's now clear now.
Okay, Ameno kana Shelter Adzoga. Are you around now?
Yes, I'm back. Say, yes, I'm back.
Okay. Okay, now continue. I think even if
Okay.
you do it fast, because now I want to go.
All right. With our example 2, what are the negations of the statement all of x2 is greater than x, and the existent x2 is equals to 2? Then the solution that we have, the negation of all of x2 is greater than x, is the statement negation of all x2 is greater than x, which is equivalent to the existent x, negation of x2 is greater than x. This can be written as the existent x2 is less than x. The negation of existent x2 is is equals to 2 is the statement negation of the existent x2
Was it
equals to 2.
was it x2 or x
I'm
squared? I
sure
don't know. Was it x2 or x squared?
it should be x squared over here.
I don't know. It's your example. But I was just asking, there was it not a typo?
Yeah, I think it was a typo. Sorry,
Yeah.
guys. We have a
It's
typo
x
over there.
squared. It's x
So
squared.
it's x squared. Where it's written x2, it should be x squared is less than x. So this can be rewritten as the existent x squared is not equal to 2. The truth values of these statements depend on the domain. Next slide. Okay, translating from English into logical expressions. Remember, we were translating logical expressions into English. Now we are translating English into logical expressions. Translating sentences in English or other natural languages into logical expressions is a crucial task in mathematics. The goal in this translation is to produce simple and useful logical expressions. In this section, we restrict ourselves to sentences that can be translated into logical expressions using a single quantifier. Next slide, sir.
That's a salad trigger food.
That's what I wondered.
Kwani
I wondered.
vana musadaro vanhu vekwamutare ke kwahonde kwaita seko kwahonde ndokusina network here. Tinovanhu vari ku kana iwe uchibve kwahondi uri muno saka uri kuti vanobve kwahonde sevanhu kwahonde vatori muno. Anyway, zviri kuitika apa ka takamirira anonzi ani sheuta, takamirira sheuta kuti adzoke handiti. Tombodawo magroup members avo vamwe alike yakanzi mikanzo ndianiko ina handizogone kuzo akanzi mikanzo something aende pekuti anenge Rambai, akanzi Rambai. I'm sure you are part of this group. Munomboitawo muchimbotaura hatisi? Havasi kutozvida zvekutaura. All right, anyway. Apa tiri zvoni izvo and last presentation taitranslate ma-English words into its logical representation. Hello.
Yes, I'm not back, sir.
Okay, it's fine. Chikomira mbicha.
All right.
Then, so here we are now translating the English statement to its equivalent what? Quantifiers. Or predicates and what? And quantifiers. So it's now different from the propositional logic. Last time we were taking the English statements to its propositional what? Logic. If then what blah blah. But now here what we want is now from the English statement to its equivalent quantifiers, or express it in what? In its quantifier. Just like that. So sheuta kana wadzoka unokwanisa kungoti tifambire mberi handiti?
Yes, sir. I'm very sorry. My network is very bad.
Okay.
Okay, example 1. Express the statement, every student in this class has studied calculus using predicates and quantifiers. Then the solution, first we rewrite the statement so that we can clearly identify the appropriate quantifiers to use. Doing so, we obtain, next slide, sir. So doing so, we obtain for every student in this class, the student has studied calculus. Then next, we introduce a variable x so that our statement becomes for every student x in this class, x has studied calculus. Then continuing, we introduce c of x, which is the statement x has studied calculus. Consequently, if the domain for x consists of the students in the class, we can translate our statement as all of x, c of x. Next slide, say. Then, however, there are other correct approaches, different domains of discourse, and other predicates can be used. The approach we select depends on the subsequent reasoning we want to carry out. Next slide, say. For example, we may be interested in a wider group of people than only those in this class. If we change the domain to consist
Asaenda futi. Mamwe magroup members muripa batsire sheuta network yakaita chimunoka down. Tibve tangopedzisa vamwe vanzwisisa. Group members, group 5. Group 5. Vari piko ve group 5. Yeah, group 5. Network yangu isiri kushanda here kana kuti? Rukwamba kwenditi isina network kai. And attendance yedu yadonha kudaro sei?
I think network iri kunetsa zveshe wasingasi.
Because attendance yedu yabva yadonha kai.
Network iri kunetsa. Ndakutotry kujoina but
Out of class of 183, tino vanhu 10. Tsaona.
Ndatopinda manje ndakachingo ndanga ndiri mupassage.
Ndimo blessing.
Tata
kumirira sandongori kupresenta here uchingopedzisa hako.
Hai ndakarova
ndiye
ndiwe kaumwe kauripo kaiwe. Ndaona senge zita rako riripo kamo blessing.
Yo mage ndakaita nana mage.
iripo se.
Nana mentors.
Aiwa president atiseyo mugrupu redu.
Hausi.
Aiwa ndakandina na
hausiriwe ndimo blessing mulambo.
Mulambo.
Ndi mulambo mo blessing hausiriwe. Ngawabatiwa ndi.
Mama bati ndakaita nana clarity. Nana clarity kushaya.
Alright. Katisire ipapo nyasho. Inozonetsa. I'm seeing some notifications. All right, it's okay. Anenge wazotonokwa down zvekudaro achadzoke. So here it was just an example. Okay, she was saying that maybe we are interested in a wider group of people than only those in this class. Like we are no longer considering only those who are in that class that we are talking about. Like this class of a student who are doing calculus, maybe you want more than that. So if we change the domain to consist of all people, we are now considering all people. We are no longer considering just that class. We will need to express our statement as for every person X. If person X is a student in this class, then X has studied what? Calculus. So if we are looking at this statement, we are saying, like here at first, we are saying for every student in a class, that student is studied what? Calculus. But now we are no longer considering students yet in that class. We are involving every person. So we'll be actually saying for every person X. So if that person exists to be in this class, then that person is learned what or has studied what? Calculus, just like that. Those are statements. Those are. So if S of X represents the statement that person X is in this class, we see that our statement can be represented as for O of S, for O of X, that S of X implies or implies what? C of X, just like that. So we are saying for O of X, so if that person S of X is representing what? Is representing a person X in the class. So we are just saying, once if you are in class, it implies that you have what? You have studied what? You have studied calculus. If you are seeing it, you are now like mixing the propositional logic there. If this then implies this, like here we are saying if then. So you know that in propositional logic, if then it means this one implies. So S of X implies C of X. So just to be a student in this class, calculus, just like that. So you'll be now mixing the quantifiers and then the logic part. So our statement cannot be expressed as for O of X, then S of X, and because it's what is of if then. Because this statement says that all people are students in this class and they have studied the calculus, of which it's wrong. Not all people are students in that class, because you are now considering all the people. But we are just saying for those who are in that exist in that class, then they've actually studied what calculus. I don't know if there is any question here. Don't know if there is any question. So finally, when you are interested in the background of people in subjects besides calculus, we may prefer to use the two variable quantifiers. So when you are now using two variables quantifier, there is the X and then there is Y in our domain. So for the statement is student X is study subject Y, then we would replace C of X by what? By Q, X, and then calculus. And in both approaches to obtain O of X, then X calculus, or for O of X, then S of X studied what? Calculus. So you see that this X is what is the student, and then the Y is what is the subject. So here that's why we are seeing Q of XY is now what Q of X calculus, because this is our what is our Y. This calculus is our Y. So you can have, this is the scenario where you have a quantifier with what? A predicate with the two variables, with X, Y. That's what it means there. So for the student X, that is studied what? Subject called calculus. So for this statement that we have initially, which says for every student in the class, that student studied calculus. And now you are referring to the what? You are now referring to everyone or to every person in the universe. You are no longer just saying that class. And then after coming up with this, and then if you want to include the subject, now you can use these two variables. So you say for all of X or for all students in that class, they've what? They've studied what? Calculus. Or we can just say if a person X is in this class, then that person actually studied what? Calculus. So those my statements iwayo zvinogona kuita sezvinovhara but ndizvozvo. So that's it for group 5. I don't know if there are some questions. Do we have some questions here? Do we have some questions? Vanozokubvunza vachazvida vanode kuzorora. Okay. Kana vanhu vasina mibvunzo ndokuti vazvinzwisisa handiti?
Yeah, I don't have any questions, sir.
Okay, what about others? So group 6, please prepare yourself now. Hatizoite machallenges otoite 20 minutes, 30 minutes takamira kuti titange nhingirekeni handiti? Vanhu muchitiza. Next year tongonobhara 0 handiti? Tongobhara 0 tosiyana nazvo. Because vanhu vanenge vachiratidza kuti havasi kuzvida zvekudzidza. Anyway, thank you team. I think we can meet on the next and our final tutorial before your exams, so that I will just bless you for the coming exams. And I think you'll be actually well equipped with everything that you need for your exam. And I think we'll also have done justice by that by then. to this module. So thank you. Have a good night.
Thank you, sir.
Good night.
You're most welcome.
Yeah, thank you. I think if you